Welcome to the Maine Science Podcast. I'm Kate Dickerson. Today's episode is a conversation I had with Seth Campbell, who's an associate professor in the School of Earth and Climate Sciences and Climate Change Institute, and the director of academics and research for the longest operating polar research and education program in North America, the Juno Ice Field Research Program. Seth's work in the Arctic and Antarctic has covered basic research, mentoring, and a lot of collaborative research about the global glacier systems and how it impacts all of us. Our conversation was recorded in April 2025, and I could have kept talking to Seth for many more hours. I hope you enjoy it as much as I did. Seth, welcome to the Maine Science Podcast. I am over the moon to have you here. I've been a fan from afar for a while, and then I roped you in on a project and then been a fan from up close. So we can get to the project I roped you in on. What was it that got you interested in science and what you're doing in particular, which is not an obvious, like Arctic studies is not necessarily the first thing that people think about. I don't know when you actually did kind of get hooked on science, but little kids don't often go with Arctic studies, what you're doing, unless it involves a polar bear.
Yeah, sure. So I'm from Maine, and my dad was an environmental scientist by training. And so that helped, I think, pulling me out of school to go do real science as opposed to learning about science was a big impact. So yeah, I remember helping put radio collars on beaver to look at the impacts of the hydropower fluctuations of the lakes we have in Maine on beaver populations. I know they cool studies on loons and trying to figure out how the hydropower fluctuations impacted loons and the fisheries. And that really got me going with the sciences. And I also had a pretty influential grade school science teacher that got me pretty stoked about science as well, which I was able to bring him to Alaska on a research expedition 25 years after grade school. So that was pretty fun. So I think those two pushes really got me going on the science. I'm from Maine, so we're used to snow as well. So I think I had a natural interest in snow and ice from an early age. And then combine that in my kind of high school into college, I really picked up climbing, rock climbing, ice climbing. And I figured out, I can actually work and play in these environments, learn about these places as a career. I mean, what better career to kind of have your passion become your career?
You grew up inland Maine, right?
No, I grew up in Mid-Coast Maine. So Noblesboro, Maine, right next to Damerscott and Newcastle. I went to Lincoln Academy as a high school student and then did my undergrad at University of Maine at Farmington. I was not the best student, I will admit. And I had a couple professors there at the time really kind of take me under their wing. Tom Easler and Dave Gibson kind of helped me figure out college. I won't tell you what my first year GPA was. It was not good.
I'm totally with you. I think college can be, especially if you haven't learned how to study, it can be really hard at first. But I also think it's really important. People end up doing these phenomenal careers, but they have this really great, difficult adjustment period in college. Basically, what I'm saying, Seth, is you're bleeding into the whole point of my podcast here, which is it's not like the only people who get to do science are people who have only ever succeeded or only been like the top-notch people, because I actually think in some ways, sometimes it's better to learn how to fail in academics so that you understand what it's like to fail in science, because that's how you push it forward.
I would agree with that. I tell this to people pretty frequently. This will be the first time I ever tell this on a podcast, but the one class I actually failed was electromagnetics, so physics 2, and that happens to be my expertise that I have spent the last 17 years bouncing around the planet doing electromagnetics. So I think it's a good example of I figured it out. It just took me a little longer, and it interested me in many ways because of the fact that I didn't quite understand it when I first started it, and I still don't understand it. There's a lot of these complexities that are really challenging with electromagnetics. So it keeps it interesting too. So yeah, I agree with that. And also, I think the other thing is science is all about uncertainty, right? Like we don't know the answers for what we're trying to understand. And I think uncertainty is really challenging for a lot of people. And so the more we become comfortable with uncertainty and not necessarily knowing the perfect answer and recognizing that there's a lot of gray area, and we're trying to sort through those gray area regions and make the best decisions based on the science that we're doing, as opposed to having the black and white answers. That's what science is. We're trying to use as much information as we can to make those informed decisions.
Yeah, I think we do ourselves a favor when we remind ourselves that people like legislators and policy people are often making the best decisions they can with the information they have at hand. And if you, as scientists, are able to then say, oh, wait, we've learned something new that we didn't know before, so you need to rethink it. We need to be able to have grace and understand, like, just because the decisions were made before doesn't mean that they were wrong. They may have been the right decisions at that time, but we have more information now. I think we've somehow lost track of explaining that.
Yeah. How many times do you hear someone getting grief because, well, you said this, years ago. Well, that's because we've learned more. So don't get stuck in the past. Like the idea is to keep evolving and keep improving, every step of the way. So I think you're also very spot on with that statement. And yeah, so I think that's part of the job that we have as scientists is to try to relay that information and relay how we've gone from the science of the 70s and 80s and 90s to today and how it's likely to evolve in the future, and to try to make clear that science does evolve because we learn more as we go. So I think that's an important part of the story.
So I'm going to jump into one of your projects, and you're going to see why in a second, I hope. You are the Juno Research Project, right? Yeah. Okay. Which I'll let you explain. But before I do, I want to say, if I've got it right, that project has been going on since 1946, which is pretty remarkable. I can only begin to faintly imagine what is different about what you're learning now, not just because of the technologies and everything else, but because of all the foundational work that has happened since 1946 with that project. So I'll let you talk about that if you don't mind, and both from the perspective of what the project is, but also I'm assuming what you're looking at, or I know that how you do the research has changed. But if you could talk about that some, it'd be a neat longitudinal conversation.
Yeah, sure. So the program, it started as the Juno Ice Field Research project back in 1946. And the idea came about from a few different folks, William Field Jr. and one of his proteges, Maynard Miller. And Maynard Miller ended up running this program from 1946 until about 2009. And I met Maynard in 2007. I was a non-traditional student, a bit older than the normal college student at that time. I think I was maybe 30 at the time that I participated in it, and got to experience it. And I've stayed involved ever since as a faculty member, returning each year. And in 2018, I stepped into the Director of Academics and Research to kind of direct the whole program. And we've since been flourishing, I think, in many ways because of how we do science and how we do education in the field. And the evolution of the program, it started as a Juno Ice Field Research project, and it started as a result of military funding. The Office of Naval Research started the same year in 1946. And the early funding was actually using the ice field kind of as a test bed for military operations. How do you work in polar environments? How can you land a ski plane? If we do an airdrop out of the plane, how does it survive certain elevations? How do our troops work and survive in that environment on the calories that they're taking in based on the distance they're traveling, things like that. But they also had this goal that they really wanted to understand glacier systems, recognizing that they're a major water supply, they're a major contribution to our system. And their thought was, well, if we want to understand the glacier system, we have to start at the source. And the source is really the high elevation region where you have most of the snow accumulate. And glaciers are like a river. They just flow really slowly. They accumulate mass at the high elevations, and then they flow downhill until you get to lower elevations where you have a lot of melt occurring. And it's like this conveyor belt that's constantly occurring. And so that's kind of, you can think of that as most of our glacier systems on Earth, that they're this massive conveyor belt of water in the form of snow traveling all around Earth. And so the idea was to develop this test bed that we could study this glacier system for decades. And that's what they've effectively done. And it's evolved over the years. Its funding sources have changed over the years, from military to NASA to National Science Foundation. It had some tougher years later, kind of the mid-2000s, but we're kind of booming right now. I think the reason we're booming is this has been a collaboration between multiple universities and faculty, really kind of a labor of love of the science community, to put time and effort into this program and to figure out how we, different institutions, can pool our resources together and do collaborative research and train students in real time to kind of train the next generation that's going to have to know about Arctic environments or polar environments and know how to work and survive in those locations, as well as understand those systems, because everything that's happening in the Arctic impacts us here in Maine, right? Like there's a thing called teleconnections, that when Greenland dumps ice from the Greenland ice sheet into the Arctic Ocean, it actually influences the ocean circulation process, and it influences our fishing, right? Because it influences ocean temperatures and water salinity and things like that. So I think that's a unique part of it. And they've done many studies over the years, but it truly is a kind of multidisciplinary program where we have people studying atmospheric science, snow and ice properties, to what's happening laterally around the ice field as well. And we also have people coming up doing polar engineering, so testing different sensors and systems to see how they work and survive in kind of more extreme, harsh environments. And I think a lot of the work that we're doing is kind of what I would call in the term domain awareness. Like you have this large-scale domain. The Arctic is just an immense area, and it's hard for you to actually have information at every single location. So What we try to do is we try to understand certain locations like the Juno Ice Field and collect a bunch of remote sensing data, in situ ground truth observations, compile that together and say something valuable about that area, and then try to upscale to other areas that we don't have as much information about. And you can only really do that when you have a whole bunch of hands on deck. Now the unique part of it is I think we have 32 undergraduate students that participate every summer. They're with us for 2 months in the summer. And then we have dozens of teaching faculty and research faculty from across the U.S. and even internationally that come to the ice field every year to both teach the students, and they're teaching by doing real science. And we have the students and the faculty contributing to real funded science projects as well. So it's a pretty cool environment to work in that regard.
Did the glacier science part of it start from the beginning, or was it initially much larger research? Or was the glacier part always a sliver of it and that has grown?
I think the glacier part was actually always a sliver of it. William Field wrote it was posed when he passed. It was kind of his memoir of his time in Arctic domains. And there's a great quote of Mander Miller asking what he thought he should do, and William Field saying, well, you should start a glacier program. Like that was in the early 40s, I believe. So it was William Field's actually boss that told William Field he should start the glacier program, and William Field passed it along to Mander Miller. But more of the story is it truly did start as a glacier program. But I think it's evolved because we tell our students it's Earth systems, right? Glaciers don't work alone. They rely on the atmosphere and they influence all the downstream systems surrounding it. And they even interact tectonics, like over very different timescales. But tectonics operate in like hundreds of thousands to millions of years timescales. Glaciers operate on tens to hundreds to thousands of years. But they all interact in some capacity. And I think as science has evolved over the centuries to decades, that's in earth sciences, that understanding that it's all interconnected. So when we teach students on the ice field, we have scientists that come up to the ice that specialize in a wide range of backgrounds, and the ideas are all working together to kind of study earth system science. Actually, this is kind of fun. I would push it beyond earth system science too. We have planetary scientists coming to the ice field because there's a lot of planetary scientists that know a lot about Mars and Europa and Jupiter, and we can actually work together to kind of understand what's happening on Earth, use Earth as an analog to processes that might occur in other planets. So now we even have planetary missions that are happening on the ice field funded by NASA. So it's been kind of an exciting past decade because of those types of evolutions as well.
I'm going to circle back to this project in a second, but I also want to give you a chance to talk about some of your other research. I alluded to how I was a fan from afar, and you were able to take part in the Warming Sea Project. I don't remember off the top of my head what exactly you were able to talk about. Just that night was a blur. Like, it was a fantastic blur, but it was a blur for me. For people who were not lucky enough to experience it, we had people who were doing research in climate based at Maine talk about their work so that people could get a sense of how this musical piece was created. So we had folks who had not actually been interviewed by the composer Lucas Richmond, but who were doing really critical, as far as I'm concerned, climate work. The intent was the audience could get a sense of how Lucas experienced talking to 14 different people about their work, right? So that was kind of the idea behind it. That was a really fantastic opportunity for these really diverse people who are doing great work in Maine. I love talking about Juno. I'm going to circle back to that, but I also want to give you an opportunity to talk about other work.
Yeah, sure. Some of the other work I've been involved in, I've spent a couple of years of my life on the ice in Antarctica since I really dove into this world. If you look at Antarctica, if you kind of use your hand, make a fist and hold your thumb out, your thumb can kind of be the peninsula of Antarctica, and then you can slice where your fingertips punch into your knuckles. That's kind of the Transantarctic Mountains, and you can separate East and West Antarctica. And I've spent about a dozen trips down to West Antarctica, kind of studying the West Antarctic ice sheet, because there's a lot of concern for West Antarctic ice sheet collapse and what that might do if you dump that much ice into the ocean in terms of potential global sea level rise. And, you look at Maine, where we have thousands of kilometers of coastline, and Portland. If you were to take just a portion of West Antarctica and say raise sea level by a meter, that would be pretty devastating to the state of Maine and many cities across the globe that most countries have ports on the coast, right? That's how society has evolved over the time, because it's an easy trade route, right? Yeah, so basically a lot of my work in Antarctica has been focused on looking at the potential for sea level rise and what we're currently seeing, what has occurred in Antarctica in the past. Can we use past ice thickness, ice volume fluctuation information that we can obtain from Antarctica to say something useful about what might happen in the future? And so that's a lot of what we've been doing. And I think one of the most interesting, bigger projects I've been involved with, it was the the Thwaites Glacier, International Thwaites Glacier Collaboration. It was a partnership between the United States and the UK, where we had about 60 funded scientists, about 100 people in total involved from across both countries, spending time on the ice over 5 or 6 years, trying to understand different components of West Antarctica ice sheet, namely on this glacier called Thwaites Glacier that drains a large portion of West Antarctica. And so we had people who were doing exactly what I said, looking at deep past, looking at more recent and the current structure, and then modeling with all the information we have, trying to model and understand what we might expect to see in the future based on future atmospheric projections and changes in ocean processes, things like that. So pretty remarkable team to get a chance to work with. And, you do something like that, you learn a lot. It's a pretty eye-opening experience to gain knowledge from all those scientists involved in it. And of course, you go to the ice, you come back, you're diving into the research as much as you can, and you spend time meeting either in person or virtually with all the scientists across all the teams. It's a big part of the science community is we spend a lot of time communicating with each other to try to learn from each other and that's part of the putting the pieces together of a big puzzle, right? I have a certain piece of the puzzle and someone else has a certain piece of the puzzle, and you're basically trying to fit all that information together. And to do that, it's a lot of communication. And I think the best scientists are good at communicating and working with others to try to figure out those puzzle pieces. So that's been a big part of my life over the last just shy of 2 decades. More recently, the stuff that I'm working on, I'm pretty excited about, directly impacts Maine. Looking at things like snowpack in Maine, we know climate's been shifting in the state of Maine, obviously, and simple things like changing snowpack properties and how much snow we get each year. And is it, instead of snow, are we getting rain on snow events, or are we just getting more rain events? And how is that going to change things like the snowmobiling industry and the ski industry? And that snow, when it falls as snow and it stays around for a while, it slowly infiltrates into the groundwater, and it also has this cycle that influences downstream ecosystems. Well, whereas just straight up meltwater, water just runs off, right? So it doesn't have as much proclivity to stay in the system. So trying to think about things like that and how it might impact the state of Maine are things that I'm trying to dive into as well, using my polar knowledge to help the state wherever I can.
So when you go to Antarctica or even up in Juno, you had mentioned earlier you're doing a bunch of electromagnetic work, and I assume that that's with the instruments that you're using to measure how thick the ice sheets are, where the cracks are, things like that. By the way, thank you for connecting why it's important to study the Antarctic and how it impacts Maine. But to back up, what are you able to take instrument-wise to study the snowpacks? I mean, the Arctic is very different when you're talking about how deep and how old the ice is compared to figuring out the change in ice pack in Maine.
Yeah, so I'll do a little basic science, right? So all a glacier is it's just multi-year snow that's piled up year after year after year that didn't melt away in the summer, right? And that basically is how Antarctica formed, how Greenland formed, how all our glaciers in Alaska and Canada formed, and other places across like South America, Patagonia, the Himalaya. Maine, obviously, our snow melts every season, right? We're a warm enough state that we have the snowfall in the winter and it melts every season. But the tools that I use to study the glaciers in Alaska, glaciers in Antarctica, or snow in Maine is literally the very same tool. I have a phone in my hand. It has a transmitter and a receiver. And that's basically what I'm using. I'm using electromagnetics. I'm transmitting a signal down through the snow or the snow and the ice if it's a glacier. And that radio wave energy travels down through the snowpack and or ice, and it reflects off of layers that have different electrical properties. So you can imagine the snow has different electrical properties from the ice, and the ice has different electrical properties from the bedrock underneath it. So if I'm trying to measure ice thickness, I end up having energy reflecting off of each of those interfaces, returning back to my receiver. And I happen to know how fast radio wave travels in these different mediums, so I can calculate things like thickness of that snowpack. I can calculate things like the thickness of the ice. And so we've done that all across Antarctica. I say we, this has been an effort for decades of many scientists using ground-based radar systems or even airborne radar systems, mounting them to planes and then flying all over Antarctica, flying all over Greenland, many places in Alaska to measure ice thicknesses. And then we fill in the gaps by modeling, right? We can use some kind of fancy mathematical equations to kind of assume if we have some certain cross sections of a glacier and that ice is moving downhill, we can model how the thickness of the ice is likely to be down glacier from those cross sections that we might have. And so that's kind of how we know about how much ice exists across the planet, is from a lot of electromagnetics. We also have information from satellite observations. The various satellites are able to tell us a whole lot of information about glacier thickness as well as glacier change. One system, the GRACE satellite, is a gravity system that has actually two satellites in space that are orbiting Earth, and they fluctuate in terms of their distance. They're following each other. And the distance they're situated fluctuates by the order of like a magnitude of a thickness of a hair. And that change in fluctuation is actually a measure of change in gravity. And you can relate that to things like a change in total ice volume of a glacier system over time. So you can imagine this system going around Earth over and over and over again, and it goes over the same location, the same track every time. And if you difference that slight change, you can derive how much the ice volume has changed over time and use that as an estimate of meltwater change from that system going someplace else. There's all kinds of geophysical methods, remote sensing methods that we use in modeling to kind of understand these systems. But my specific method is what we call ground penetrating radar that I am using to measure snowpack thickness in the state of Maine. And of course, snowpack thickness, if we think about snow, you have a thickness, but in Maine, we can have a light, fluffy snow, right? That like you can't make a snowball out of, or you can have that really dense snow that's like a perfect snowball. It's got a little bit of wetness in it, right? And that wetness has a big that density of the snow and the water content, the wetness actually dictates what we call snow water equivalent. And snow water equivalent is basically if I was to take a certain thickness of snow and melt it down into water, how thick would that water layer be? And that's one of the challenges that we have is as snowpacks get wetter and wetter across the planet, it actually is harder to measure snow water equivalent of wet snow than it is of dry snow. So a lot of the work that I'm doing is to try to hone in on understanding that snow water equivalent value because of the wetness that's being added to snowpack because of those warmer temperatures. And when I say harder to measure, we can be off by estimates of like 50% of our total snow volume, water volume, which is pretty big, especially when you think of billions of people rely on snow. Like I think like a third of the human population relies on snowmelt for water consumption, right? So that's a pretty significant uncertainty when you're thinking about a humanitarian perspective, or you're thinking about how is that going to impact us in the state of Maine with flooding risks. I have a friend of mine, Sam Roy. He was a graduate student that I worked with in Maine years ago, and we're still close friends. And for years, he was involved, he still is involved in basically developing flood estimates, potential flood every spring for where we are likely to see flooding based on those snowpack properties. And so that's one of the things I'm trying to do is trying to help him improve that spatial understanding and temporal understanding of snowpack and where that water is going to come from each year.
I'm so glad you mentioned that you're working with Sam, because I was thinking that you mentioned in Antarctica, right? It was a slew of all different types of scientists and all the different things you were looking at. Like it was this huge community and you got one focus. So it's the jigsaw piece, right? It sounds to me in Maine, what you're trying to figure out is, I would call it really basic knowledge of the types of snow so that you can make these measurements. So do you have a jigsaw puzzle of people that you're directly working with this, or are you doing the work and then other people take pieces of it and do their work? Do you know what I mean? Like, is it formed as a group, or do you all know about each other and you're doing your thing and then you pull as needed?
I think it's a little bit of both, actually. That's a great question. You always start when you put these science proposals together, say, hey, I'm going to work on X, Y, and Z. It generally always starts with a team. And, each team member has kind of a network of people they work with as well. So that's your kind of extended team. But I think every project I've ever worked with, that team's expanded every time. And that's one of the beauties of science, right? You're not constrained by, I don't have to just work with people at University of Maine. I can work with any scientist across the U.S., any organizations in the state of Maine that are keen to understand the systems we're studying and that might want to use the data or even have me help them collect some observations or team up, cost share resources to make it more economically viable for what we're trying to get for information. I think that's the beauty of the science field as a career, is that you can build those collaborations. But I do think it starts with a team, but you're always kind of expanding out. And when I write a proposal, I always try to have an end game. Actually, I'm teaching a proposal writing class right now at UMaine, and it's for graduate students. And it's not just for them to learn how to write their thesis proposal and their dissertation proposal. It's like, if you have any job, you might have to propose something to your boss of what you want to do, right? It's a true skill that to kind of understand how you might pitch an idea to someone and make it valuable to someone or show the value of what you're trying to do. And part of that is the outcomes, right? What do you expect for outcomes? It's not just, I'm going to develop this product and people can use it, right? You want to know what your end users are as well. And so that's a big part of trying to make sure you know who your end users are. And, taking it a step further of saying, okay, this data product, we can specifically plug it into, I'll use that example again, to our flood predictions in the future, right? So that's one example. It could probably specifically, I haven't done this, but it could probably very specifically be plugged into our understanding of agriculture, what we might expect for groundwater levels and things like that when we're thinking about agriculture and forestry applications and things that are of economic importance, environmental importance to the state of Maine. So I think it's a little bit of both, but it definitely is important to kind of think about your end game as well.
Yeah, it strikes me that there's a fairly large range of areas where you've done the research and people can kind of go back and figure out how do we apply what you have figured out. I'm also thinking, right, if we don't have the snowpack and have kind of a slow release of water and it's just these events. A couple of winters ago, right, we had these massive windstorms and it wasn't really cold. So one of the biggest issues we had, especially on the coast and even into Bangor, were these trees where in other Decembers and early Januaries, the ground would have been frozen enough that the roots would have held the trees in. And if we don't have colder winters and colder times and the ground is wetter because of that, that strikes me as a much bigger risk of things that we aren't built for. So it seems to me that your research could help feed into better understanding that.
Absolutely. Yeah. And some of the tools that we use could be useful for that. So some of the most recent tools that we're acquiring, we haven't acquired it yet, but we're very excited about it. We're acquiring this LiDAR system that will be mounted to University of Maine's plane. That's a top of the line LiDAR system that can be used for very detailed elevation mapping, forestry mapping applications, agriculture, coastal erosion, things at like centimeter scale. So from like looking at post-damage events and trying to understand where do we need to put time and effort in. We had this LiDAR survey at this previous time, and this is our second LiDAR survey. This is how much damage occurred at this location, and we think we have this unstable region. Using those tools and instruments that we've developed, I kind of have a vision of making sure that equipment is also being used for future needs in the state.
LiDAR is using laser instead of sound, right?
Yeah, exactly. Yeah, so you're shooting a light basically bouncing off of a surface, and we know how fast light waves travel in air, and shoots millions of photons per second, basically. So you create this three-dimensional picture of the subsurface from a plane. And the cool thing about LiDAR, well, there's many cool things about it, but one cool thing is some of those photons bounce off of tree surfaces and some of them penetrate all the way to the ground. And so you can do what we call a bare earth model. We can actually model the earth underneath the ground. So that's how we figured out all these beautiful moraines all over the state of Maine from prior glaciations from thousands of years ago that were just covered by vegetation. And that's how they've been able to map out incredible archaeological finds across the globe under dense vegetation just by having that ability to kind of map what's underneath the vegetation cover above. But we can also use it to estimate biomass index. And when we couple it with other sensors and systems, we can do some pretty sophisticated work from an agriculture and forestry perspective.
You mentioned students a couple of times now, and I always feel like I'd be remiss if I didn't allow you to talk about in your role as a professor, right? Like I lean heavily on the research that when I talk to people, because that's what I find most fascinating. I just think it's really cool. But I also know that you do a ton of research with students and mentoring with undergrads and graduate students. So I guess I'm curious, like how soon do you get undergrads? Do you get people who walk in and they've been on campus for a week and they're like, I found out you do Arctic research, I'm in. You can pick either one to talk about or both. But I think it's another example to me of, I know you're with the Climate Change Institute. The Climate Change Institute is literally world renowned. You get collaborations with people from all over the world. And I think it's a really good opportunity to remind people that you guys bring it. And my guess is you've got some students who don't quite realize how impressive it is until they get in on it.
Yeah, quite possibly. I have two roles at UMaine. So I have the director hat for the Alaska program, the Juno Ice Field Research program. And then my role at UMaine, I have two affiliations, one with the Climate Change Institute, and then my teaching role is with the School of Earth and Climate Sciences. So all my classes that I teach are through the School of Earth and Climate Sciences. And a few years ago, UMaine started a program, a research learning experience for undergrads, where it's basically designed for incoming freshmen. And so I've been involved in that course that we teach at UMaine every year since that program's inception. So I'm working with our first year students, introducing them to science. And really that course is designed around just getting them psyched, getting them jazzed about science and trying to answer questions and realizing it's okay to not know the answer and that we're all lifelong learners. Like that's really what science is about. I'm just a lifelong learner, nerd at heart, just trying to figure stuff out. And when you enjoy your job, that makes it easier to do. So I work with the first year students, which is great. I also teach grad level courses. So I have kind of more advanced courses that I teach where students are learning how to use the geophysics tools that we use and proposal writing, kind of taking their science knowledge and translating it into something valuable and product that can be potentially raise some funding for a specific research project. So I enjoy working with that range. I will say my favorite part of the job is working with the students. My graduate students have this thing where we have this email text chain. It's a science of the day. And it's the best thing. They send everyone, our whole team, like some screenshot of some cool figure they made, something they figured out in their science. And I'll say our students are the ones that are actually doing the incredible research. Our graduate students particularly. When you get into a role where you're writing proposals and trying to get science done, it turns out that I don't actually get to do a lot of the science. I get to do a lot of the mentoring and trying to help the students. And they come to me with these incredible results, and I help them tweak it and revise it and, work on suggestions on how to improve it and, figure out the next steps. But these graduate students are the ones that are really in the nitty-gritty detail doing the programming, looking at all the data and trying to pull out the important relationships that we're trying to understand. So I think that's one of the reasons it's truly, as opposed to answering phones and answering endless emails. Every day when I look at my calendar, I'm like, okay, I have 3 really good hours because I have 3 meetings with 3 different graduate students on 3 different really cool projects. And they're going to come, and I know they always come with really cool results and observations. So I think that's kind of the cool part. Back to your question about whether students quite understand the resources that they're gaining or the experiences they're gaining. I think a lot of students don't necessarily know that, and that's fine. I think a lot of the programming that I've been involved with, both at Maine and external, I've been working with a lot of marginalized students as well, trying to give students that come from low-income backgrounds, first-gen backgrounds, opportunities to kind of fall into this career. Traditionally, polar sciences, Arctic science, geosciences has been certainly underrepresented in terms of marginalized community members for a number of reasons. One, it's a cost to get into that community. If you're a field scientist, having the equipment, things like that, required to take some field capstone course that costs money. So there's a whole bunch of barriers. So the group that I've been working with has been working on trying to reduce those types of barriers to students. And I've also very much enjoyed that. And I think those students certainly wouldn't have known. I didn't know this was a possible career when I was in high school. I didn't know this was a possible career when I started my freshman, sophomore, junior year. I didn't figure it out until I was actually became a climbing guide and figured, I could probably merge this with my science interest and work in the mountains. Yeah, so it took me many years to figure it out.
Yeah, and I think that's what I was getting at is very rarely do people, when they go to college, end up doing exactly what they thought they would when they were first starting, nor do they necessarily end up doing what their degree program is in. And I think having the opportunity to have those early undergraduate experiences is good. I've told people before, like, one of the best things I learned was that I did not want to be in a lab. And I learned that when I was an undergrad, and that saved me a lot. It's good to learn that. And so if you don't have those experiences, man, you get stuck. So yeah, I think that was what I was trying to get at with that. All right. I want to get back to the Juno thing. If I'm doing my math right, next year is 80 years, right?
Yeah.
And so that's 80 years of consistent research every year with an assortment of funding. First of all, I'm wondering if you guys are just going to do anything fun to celebrate 80 years, because that is a not small milestone, especially if, let's be totally honest, in a young country like America, that's pretty great. Before we started recording, I said I was going to talk to you about this. I think it's really important that we discuss the value and the importance of long-term basic research funded by the federal government, because we don't know what we're going to get out of it, except that we know we're going to increase our knowledge. And it strikes me very much that 80 years of research in one place where it started as a military thing with a little bit of glacier on the side has really transformed our knowledge and helped the country in all sorts of ways. So I'm going to let you kind of run with that a little bit so you can talk about it.
Yeah, I think one of the unique things that the Juno Ice Field Research program has provided, you can't go anywhere in the United States and speak to a polar scientist and ask them if they've heard of the Juno Ice Field Research program and have them say no. Like, everyone knows the program. A large percentage of faculty, it's been around for 80 years, so a large percentage of faculty, students that have stayed in the field have been a participant, a research scientist, a teaching faculty member on the program. Every person that goes to the ice field signs the rafters on all the buildings we have on the ice field every year. And so it's just an incredible assortment of names on the ice field. You asked about the 80th year. One of my favorites was Steve Squires. Steve was a Juno Ice Field alumni, and most people probably wouldn't know who he is, but he was the chief scientist for 2 NASA rover missions, and now he happens to be the chief scientist for Blue Origins and was a professor at Cornell. And he gave one of our keynote lectures at our 75th reunion. We did a virtual 75th, and we had people attend the program that were in the program in the 50s. They're still so excited about this program. So the camaraderie and the relationships and the inspiration, I think, and the long-term community building, I think that's really the contribution. And we're doing good science on the ice field, and it's an incredible training opportunity. We're doing really cool science on the ice field now, and really good science has been in history. But I think the bigger impact is building that camaraderie across the broader science community in the U.S. for scientists to kind of have a network. I mean, you could go to many careers, but the polar science community is a pretty small community. And so recognizing it's as small as it is, people, I think, are legitimately very close. And I think JERP is a big part of helping people build ties to each other. So that's the impact. And so the 80th, I'm guessing we will do something for the 80th. We'll probably do another virtual. The 75th virtual is a big hit, a big success, and I'm sure we'll do something on the 80th as well. You asked about the funding, and I've been involved in sciences for shy of 2 decades now, chasing funding and trying to figure out how to fund the science that we do. And it's actually operated by a nonprofit, technically. The nonprofit's a Foundation for Glacier Environmental Research. And the beauty of that is it helps bring people together. In the past, I think universities, organizations traditionally were working more separate. And I think in the future, we're going to have to work harder to figure out how to team up to get things done. I think that's going to be incredibly important. Our team has been doing this for a very long time, and we're excited about that. Trying to be as inclusive as we can and pull people in. Sometimes it burns you, but 99.9% of the time it doesn't. The benefits far outweigh the potential losses that you might incur by teaming up. So I think that's one important thing to consider, regardless of what happens with federal funding in the coming decades. We have a huge amount of existing knowledge that we can run with. I have data sets that we can easily dive back to with new processing techniques. So that's what we're doing. We're going to be doing that. We're going to be diving into the science, what information we currently have. And I think that's incredibly important. The thing that I think a lot of us are really concerned about with the current funding concerns is the loss of our next generation of scientists. And I think many of us are trying to reconcile that and the fact that scientists, most of us are just out there to try to make things better for people, to be honest. I grew up in an average home in the state of Maine. Our meat in the freezer was deer meat or moose meat or trout or small game. We did okay, and that's how most of us grew up in our community. So I grew up in a very conservative home. And I think nowadays people are starting to recognize the importance of science for all the state of Maine. Whether you're working on the coast as a fisherman or working as a carpenter or working in academia, teaching students in grade school through high school through college, or working in agriculture or forestry. Science is pretty important for all of us. And I think that's the thing that most of us are fearing right now, that by losing that generation of scientists, we know new viruses are going to come up. We know new issues are going to come up from health of our crops and health of our forests. And we know we're going to have water resource issues and pollution issues. And we need scientists to be able to help with those issues. And I think the problem we have is that right now our federal government is kind of a short game process where, things change every few minutes depending on who's calling the shots. And science is a long game process. And I think across the board, we need to work hard to kind of bring people together to recognize that. And so, I'm spending a lot more time trying to help people see the value in science and how it helps everyday life. And I think the science communication piece is really important. And in fact, like the Juno Ice Field, a big part of the curriculum that we teach the students is science communication. How do you explain the science to someone, to your family, to your friends, to really anyone, right? It's just basic science, trying to get those points across. Teaching students how to do an elevator pitch of their science and what they're working on. Those are incredibly important skills to be able to explain the science to people. And so the more we do that, I think the better off we're going to be in the long run. I can't say one way or another where I think the funding is going to go. I have obviously very significant concerns. Let's say in the past 4 months, my workload has probably increased by 25%. Just feel like I'm doing a little bit of a whack-a-mole, trying to figure out what to do next. But my focus continues to remain on my students that are doing incredible science work and making sure that we continue to get that science message out to show what we're doing and how it's important to society, how it's relevant to Maine, how it's relevant to the U.S., how it's relevant globally. And I think the only other thing I might say is when you get into this community that I'm in, it's not just a community that's just Maine, right? It's a global community. And nowadays, you can't live and work in a bubble. We are a global economy. Science and the challenges that we face are often global. And it takes collaboration and willing to be at the table with people across the globe. Even if you don't agree with what they're thinking, you still have to join the table. And I think there's a lot of fear right now that we're not even sitting at the table with some of the global discussions that need to happen. And that's not a good place for us to be in, I don't think. So I'm willing to meet and chat with just about anyone. And I think that's important to try to have that perspective moving forward, that we need to make sure we're at that discussion, because the situations we're dealing with are very much global in scale, and it's going to take global action to kind of deal with some of the things that we're dealing with.
I don't think there's a better way to end this conversation, or at least to have a to be continued, than ending it there. I think that was super eloquent. And I think it was pretty clear to me. The focus of this podcast, obviously, are people who are doing work in Maine. But one of the things I'm really trying to get people hopefully to hear is that we focus on Maine and the research that's happening in Maine, but that also includes the rest of the world. And I think really sum that up really well. And we aren't by ourselves out here. Like, I want to focus on Maine so that people know that we do this work here, but we actually do have impacts all over the world. I appreciate you giving me just a little bit of your time, especially given that your workload has increased so much in the last couple of months. I'm always over the moon when people are willing to give me a little bit of their time. And I'm hoping that our conversation will help build a little more foundation for people to better understand the science that happens and how critically important it is. I mean, what you just said is kind of how I feel about all of it.
Awesome. Well, thanks for the time. I'm psyched about everything you do. So mutual respect in the stuff that you're working on. So
it's good we all find our spots, right?
Yeah, exactly.
I get to talk to people doing amazing work with their students. So I appreciate it.
You're doing a great job sharing the science. We need you and 20 more of you.
Thanks for listening to the Maine Science Podcast. Make sure you never miss an episode by following us on your podcast platform of choice. And please leave a rating and review. It will help more people find us and help spread the word about some of the remarkable people doing science in Maine. The Maine Science Podcast is recorded at Discovery Studios at the Maine Discovery Museum in Bangor, Maine. The Maine Science Podcast is executive produced and hosted by me, Kate Dickerson, and edited and produced by Scott Loiselle. And the Discover Maine theme was composed and performed by Nick Parker.